All right, guys, so I want to explain a little bit in depth what reverse Polish notation is and what is it good for, why do we use it in computer science, and how this is used by compilers or translation software. So first of all, reverse Polish notation is just what we call in postfix notation, and we're going to see what that means later, because there are three different types of expressions or algebraic expressions that we can create: infix, postfix, and prefix. So we're going to see what that means in a little while, and I want to explain how these postfix expressions are good for computing and why we use them in computer science. So to understand that, I think it's necessary to make an association between the concepts of compilers and interpreters, which are just programs or software that is meant to take as an input source code, right? And by source code, I mean instructions that are written in a specific programming language, and they are in a specific file or just as an input to these programs. And these compilers and interpreters, what they do is they execute the instructions one by one in the case of interpreters, or they create what we call object code, which is executable code for the machine, the specific machine that we have, and that's done by compilers, right? So one of the main differences between interpreters and compilers is that interpreters execute instructions after they analyze them. If they are correct, they execute them. But compilers, what they would do, they would check the entire input of the complete source code file, and if everything's right, then they would generate the object code, right? So when we say that they analyze the source code, what we mean is they start checking many things. So in another video, I will explain what compilers and interpreters do exactly, what are the different stages of analyzing that source code. But here I'm just going to focus on what we call a postfix RPN notation for the expressions that we find in a programming language. So usually these instructions come in the form of statements, and some of those statements are things like assignments, right? So when we have a variable and we assign to that variable an operation, and usually we have maybe simple or complex algebraic expressions to when we see those statements in the programming languages, right? When we're trying to create a program. So for us, for humans, the infix notation is the most common because that's the way they teach us how to make operations, right? So what I mean by that is when we try to create like a statement, let's say that I want to assign to a variable x the result of adding two other variables, right? So we usually represent these operations like this in the infix form, since what we do is we have, for example, for a binary operand like the addition, like plus, right? What we do is we have first an operand, then the operator, and then another operand, right? And what this means is I want to add first this value with this value, and that result should be then assigned to this variable, right? That's what I'm doing here. And this way to represent things, this it's this y plus z or z is what we call an infix expression, right? This is infix. postfix expression is something else. I mean, it's another way to do this. And what we do in postfix is we put the operator after the operands. You might have seen this in some calculators. Even some programming languages do this. So this would be another way, right? So let's say that this is the expression that I have, and this means exactly the same as this, right? But these are just two different ways to express the same operation, right? So in postfix, what I have is the operator is after the operands. In infix, the operation is between the operands, and there's another word called prefix, where I have first the operator and then the operands. So in this case, it would be something like this, right? So those are the three different types, and the reason why we choose to understand how to change from this infix to this postfix is because what we want to do is make it easier for the compiler to execute these operations. So when we are, I mean, when we try to write a program that executes this, it's going to be more complicated to analyze the expression because if it's, I mean, this one is easy because we just have two operands and one operator. But once it is more complex, then you know that when you analyze one big expression, like, I don't know, let's do anything here. Something like this, right? You need to, when you're going to evaluate this expression, you might need to maybe check this operation many times, or check this expression many times before you can actually get the value. And what I mean by that is, let's just make an example here. So if I have this complex expression, right, this right here, I need to analyze the precedence of the operators first. So I know, for example, that the first operation that I should make here would probably be between these parentheses, right? And then I evaluate this, and then I go back and check what else I have left. And I have to do that once and twice and thrice, right? Until I get the last value, right? Or maybe what I should do is just have in mind the, oh, this operation is impossible. Maybe have an X here. You know, like, for example, do this, which is the higher precedence, and then do this, which is the highest, and then do this, and then, right? So a program or a computer program that it's to analyze this expression would have to do that over and over again, right? So I don't want that because I want to make things easier for the computer and for the programmer who's going to tell that computer what to do, right? So it's easier if I just do it in one run. So when we have postfix expressions, it's easier to do that because I can make use of what we call a stack to run this entire expression or evaluate this entire expression without having to look at it more than once. Okay, that's the main reason why this is done. And there is another one which is free prefix, but we're just going to know that that exists. We're not going to analyze that. There's obviously a way to evaluate that as well, but it's, I mean, we care about the postfix or the reverse Polish notation because that's the easiest way to implement in an algorithm so a compiler can transform from infix to that expression, and then so the computer can evaluate that expression. So now that we have seen that, let's see how this works. So if I am going to change an expression from the infix to postfix, the first thing I need to have in mind is the precedence of the operators. So this is the precedence that we have for math, right? For algebraic expressions. And you're going to see why I put them in this order. So I have first exponential, right? Then I have in the same level times and divide and division. Then we have addition and subtraction, and then we have association, or the parentheses that are made for grouping, right? So the way you do it is you're going to create a stack of not the operands but the operators. So you're going to create a stack of operators so you can then the way the stack works is that you start adding things right here, and when you're going to take things out, when you pop things out, is actually what the term that we use, then it should be on the last, right? The last element should be the one that you take out. So this is the last in, the last in first out. That's what a stack is. The last one that came in is the first one to go out. All right? And having that in mind, then we know how the stack works, then we can create a stack for this operation. So let's say that I have this stack. It's empty right now. And it's going to be full of, or it's going to be filled with operators. So the operators are in this expression, are this, this, and this, right? Those are the elements that I'm going to start adding up here. And as I said, we start reading from left to right, right? So when I find an operand, I just put it in the result of my transformation, or the output of this algorithm. So let's start with the first term. So I start looking at the A, so this is an operand, then I just add it to the result, right? So I have A. Then I find the first operator. So since there is nothing here, it should be the highest precedence, so I'm going to put it there. So I'm going to have the minus here. Then I find B, I put it in the output. Then I find times. Now the question is times higher precedence than the minus? If I check here, yes, this is higher than minus, so I put it in the stack, right? And then I check C, then I have C, then I check this one, is this higher precedence? Yes, so I put it in the stack. And then I find E, right? So since I finished the expression, what I do is I start popping things out of the stack. So as I said, last in, first out, so this is going to be first this out, then this out, and then the last one out, right? So this is our postfix expression, right? Now, this one is quite simple. I'm going to keep it simple for just the explanation. I'm going to do some other examples here so you can see how this works. But we can also create another representation of this using what we call a binary tree. And this is a special binary tree, which in the case of a compiler or an interpreter could be the syntax tree. Or it could be, it would look similar to what we call the parse tree, which is the result of parsing, of the parsing stage of the different stages in what the interpreters and compilers do. But I'm going to explain that in another video. So to explain what's the parsing stage, there are 4 stages actually. It's lexical, syntactical, and semantical analysis, and code generation. So each one of those is going to provide a an output, and this syntax tree or parse tree is the output from the syntax analysis part, or the syntax analysis stage of compiling or interpreting, but that's another subject. So I don't want to mess this up. So this output, we can construct this by taking this expression and making it parse tree. So the way we can do that, I mean, you can just analyze the expression, and you see that the first, for example, from the infix, you see that the highest precedence is the power, so that's the one you take on the leaf, right? So you see that this operation is the one. Let me just show you. This operation is the highest precedence, so that should be the leaves, right? And then we have the second one is this, so that should be the other node, and then we have B, and on the other side we have the result of this operation, and the least precedence is the minus, and that's what we have here. That should be the root. So in these trees, the root should be the lowest precedence and the last one that is going to be evaluated. So I'm going to explain here now one algorithm that we can use to change or to get that tree out of a postfix expression. So the way you do that is you kind of like have let's call it a horizontal stack. So I'm going to do it here. And what you do is you start again reading from left to right, and you're going to add to the stack both operands and operations and results of operations. So let's put the expression. Well, one thing that you need to analyze before we do that is that the equivalent to, let's say that I have this infix, right, a minus b. The equivalent for this in postfix is going to be ab minus, right? So that means when, for example, when I evaluate a postfix, what I do is I take the second operator and I put it in the end, right? So this is a minus b. And if we have a tree that is representing the same thing, then this is what we have, right? We have a minus b. So when we want to take something like this, ab minus, and we want to make a tree out of that, what we should do is use the operation and then have the second one as the right leaf and the first one as the first leaf, right, of this tree. Well, in a tree, binary tree, these are called nodes, right? And these are called leaf nodes because it's a tree, right? So the ones you have on the branches are the leaves. This is a leaf. So what we want to have is, if we want to represent this postfix, right, in a binary tree, then what we should do is have this element on the right and this element on the left, right, because it matters the order. So with that explanation in mind, then we can do the operations here. So let's just start here. So I start reading left to right, right? So if I find an operand, what I should do, I just put it in the stack. So I find an operand A and I put it in the stack. I find the operand B and I put it in the stack. I find the operand C and I put it in the stack. E and I put it in the stack. Now, when I'm going to pop something out is when I find this element here. And what I do is I take, as I said, I take the operation as the node, and then what I do is I put on the right the first element that I take, and on the left the second element that I take out, right? So I just did that, right? I took E and C, so they are no longer in the stack. But what I have now is the result of that operation, so I put that in the stack. So let's keep that format. So I'm going just to show what the tree, I'm not going to draw this tree here, so I'm just going to point it there. So now I have this one, and I continue looking for things. So I now see that I have this times, right? So that means that this entire subtree is going to be now the right side of the next tree. So let me just do that. See if I can move this thing here. Actually, I can't. So let me just copy that and try to move this away from here. No, didn't work. So let me just do it again. So what we had was C, E, and this operation, right? And now this became the right side of the tree of this times with the next element that was the B, right? Now I have this whole thing, so I take out this B, and I have this whole thing in the stack right here, right? And now I find the other operation, which is this minus. So what I do is I take the both things, right? Now this is this subtree, this whole thing is going to be my right leaf, and this is going to be my left. So what I do is, and I can get rid of this. I'm gonna get rid of the stack now because I'm okay. Maybe I can move it here. No, I can't. Yeah, let's do this. And what I have now is my minus here and my A here, right? And now I pop the A, so the stack is empty, so that means that I have finished everything. So that's the way you construct it. So the algorithm could be explained as go from left to right, and when you find an operand, then you just put it in the stack, and when you have an operator, then you create a subtree which is going to take the last two elements of the stack and is going to make the last element as the right leaf and the next element as the left leaf and the operation as the node, right? That's it. So I'm going to erase this. So let's just review that. And this is what we have. So this is the postfix. Oh my god, this is wrong. So we have A, B, C, E, and then we have power times and minus, right? And that's equivalent to this tree, right? So let's do another thing, which is evaluate the expression that we just got in postfix and make it an infix. So we have we have A, B, C, E, power times minus. So the way we evaluate this expression, this postfix into an infix, is we also use a stack. but this time the stack is going to be filled with operands, and the way we pop them out is with operations. Again, we read from left to right, and this is what the compiler would do if we wanted to just try to evaluate the expression. Well, that would, yeah, it would be an interpreter. The interpreter would do this. The compiler would just create the object code. So from left to right, so if I find an operand, I put it in the stack, and if I find an operator, I would take the last two elements and then execute that operation and put it back in the stack. So first, let's go here. I find A, so I put A here. I find B, I put B here. I find C, C, E, E, right? Then I find an operation, so what I should do is take the last two elements and make that operation, right? And then put it back in the stack. So what we will have is C to the power of E, right? Because that's the way I do it. I take the last one and I put it on the right, and the left one and I put it on the left, and then I put the operator in the middle, right? Just like we did in the, or similarly, it's similar to what we did in the tree to find the tree, right? So and I put back that in the stack. So what I would have in the stack would be something like this, then B, and then A, right? Then I go back to the expression and I find time. So what I should do is take this, make it the right part, right? And this, make it the left part, right? And I just did that. And then I put this back in the stack. So what I would have is this as a stack. And then I find this operation, and what I do is the same. So A, B, right? This would be the result in the end. Now, if we had values here, we would have just one result here, but since we don't have values, we just have variables, then we get the original expression, right? Now, the second part, to where I say that I'm going to evaluate the tree, there are three ways that I can evaluate it. I can use, again, postfix, I can use infix, and I can use prefix. But we care about the first two. So postfix is, it is solved, or what this means is left, right, root. Infix means left, root, right. And if we wanted to do this, it would be root, left, right. But let's just do this too, or maybe just the first, because with the other one we would get the original expression. Now there is a way that I can take, there is an algorithm to take this infix and make it this tree. But I want to do that maybe in another video, because this is now almost half an hour. So if we are to evaluate this, what this means is first evaluate the left, then the right, and then if you have solved all the left and the right, then do the root. So let's look at this one, this tree that I have here. So I have the first part is this, right? So if I check the tree, the first node is this. So I can start evaluating the left. Now, if there is nothing under the left, then I can solve this by just writing what I have there, right? So I have A. So A is the first left solved. Then I'm going to solve the right. But the right is not, I cannot solve it right away. I need to solve this subtree, right? So this subtree, to evaluate this, I need to evaluate first the left. So the left is B, right? So I evaluate the left, and then I try to evaluate the right. And the right is this other tree. So to evaluate this subtree, I need to evaluate first C, right? Because that's my left. And then I evaluate the right. And the right now it's E, so I can evaluate E, right? Now I can, since I have already solved both left and right, now I go to the root. And that means I use this symbol, right? Then I have already solved this subtree, which was the right. Now I can go back and solve the root, which was this, right? And then I do the same and I go back and I solve this, and then I got my postfix expression, right? If I were to use infix, well, it says here left, root, right. So here it would be left, then root, then right, but the right is this subtree. So I need to evaluate first left, so it's B, left, then root, and which is this, and then right, but the right is a subtree. So I do first left, which is C, then root, then right, and that should be it, right? Because I already solved both on all the three. So this is the infix, right? So with these trees, you can get any of these operations, and I just showed you before how to take from postfix to the binary tree. Now there's another, as I said, there is another algorithm to create the tree using the infix. Let's try to do that. So in the infix, what you do is again left to right, and what you do is you make the simple case the general case. So when we have this is what we want to have, right, in the tree. So the way to do this using infix is you first you need to evaluate this from left to right, and then start looking at the lowest precedence and the last operand, sorry, the last operator that you're going to have. So in this case, let's look at this expression. And what I do is I start analyzing this from left to right, and I find the one that is the last operation that I'm going to perform. In this case, the last operation that I'm going to perform is this minus. So I make that as the root, and then I put the leaves left and then right, and my right here is going to be all this expression, right? Now I need to solve this expression, so what I do is I do the same. I find the operator as the node, so I have now this operator as the node, and I take the left here and I take the right here, and I do the same here. I have one operator and two operands, so what I do is I take the operand as the root, and then I take the operator as the root and the operands on left and right. Yes, so this is the way we create the tree. All right, guys, I think this was enough so you can understand what infix, postfix, and prefix, if you want, means, and how the reverse Polish notation, which is a postfix format, can help the compilers evaluate expressions in just one run. So as you saw, if we use a stack, we take expressions from left to right, and we can evaluate them to get the final result, right? And we also saw how to change from infix to postfix, and how to take from infix, which here we checked how to take from infix and create a tree, and how to create a tree from postfix, and how this tree can also help us get back to the postfix, infix, or prefix, right? So with this in mind, I think you should be ready for some exercises, and I'm going to leave that for another video. Take care. Bye-bye.